afternoon, everybody. Welcome back to MAIN-iac Science Labs. I am Mr. Andy from the St. Johns County Public Library System, and today we're going to talk about science. Now, today's particular subject is going to be circuits, simple circuits. Electricity. Where does it go? How does it work? How do you turn it on and off? Stuff like that. You know, electricity powers things in your home using a simple loop. A wire carries electricity from a power source to the thing being powered, then back to the source. And this loop is called a circuit. Have you ever thought about how the lights in your house work? Well, you have a magic switch. You pop the switch, they turn on. You flip the switch down, they turn off again. But why? Electricity. There's a circuit happening behind the walls of your house that you can't see that's making the electricity travel to the light bulb and back again, powering it on and off as you open and close that switch. So most homes have a wire coming to the home from the electric company that connects to the electric meter, the little thing with the spinny thing. Some of them are digital now, so you don't see the spinny thing anymore though. I used to be fascinated by that spinny thing when I was a child. Well, that goes into that meter, which goes into your electrical box, which is basically a box full of switches that turn the electricity on and off to the various circuits throughout your house. There's one big switch that turns the entire house on and off, and a bunch of little switches that turn on and off individual things. So that light switch that you have in your bedroom, let's say, is on its own circuit. That circuit runs from that box through the walls to the light switch in your room, from that light switch to the light, and then back to that box again. A full loop of electricity. Now when you turn the light switch on, that loop is made solid, made a whole entire loop. The electricity travels through it and turns on the light in your room. When you turn the light switch off, it breaks that loop, takes it apart, so the electricity stops moving, the light turns off. And all the appliances and different electrical components of your home work on basically the same concept. So let's take that idea and let's break it down into something a little more simple, like a flashlight. You guys have all seen a flashlight. You've used a flashlight. You play with them at nighttime, when you go camping, when you're reading a book under the covers at night. Flashlights come in handy. And we know that this little switch turns them on and off, but what's actually happening inside the thing to make it work? Well, I just happen to have a handy dandy little diagram here that will explain that to you. If you look at this diagram, you have batteries inside the flashlight, and there's a wire that connects to one end of the battery, the negative end, and runs all along here to the switch, which can open and close that wire. Then it continues on to the light bulb, from the light bulb to the positive part of this battery, through that battery to the negative part, to the positive part of the other battery, or however many other batteries you may have, and on and on. So when the switch is in the on position, this loop is a continuous loop, sending energy through the wire, through the light bulb, through the batteries, around and around and around until the batteries run out of energy. Now when you take that switch and you put it in the off position, the loop is disconnected, the light turns off. It's really that simple. Kind of cool though, isn't it? Here's another example that's even simpler to look at. Two batteries, positive and negative, connected to each other. A wire from the negative all the way through to the light bulb connected to the battery, and this is our switch. When you open the switch, the loop is broken. When you close the switch, the loop is closed. Electricity travels, powers your light. It's pretty cool. So what we have here is a little bit of a little history lesson opportunity here, because there was a famous physicist really long time ago who came up with the idea for this stuff. One of many, but he succeeded in 1800 to make what he called the Voltaic Pile. And now that man's name is Alessandro Volta. He was an Italian physicist, and in 1800 he published a paper talking about the Voltaic Pile, which is how he got a battery to generate electricity. How does one of these things make electricity happen? Pretty cool stuff. He figured out that if you had two different types of metal, and in between those types of metal you had what he refers to as a moist intermediary, in this case electrolytes, chemical reactions will happen between those metals and cause energy to occur, electricity to occur. Let me see. The Voltaic Pile is one of the earliest forms of batteries, invented by Alessandro Volta in 1800. He's quoted as observing electrical phenomena that were caused by two different metals joined together using a moist intermediary. Pretty cool stuff. So the battery was based on this general concept, and if you really wanted to get deep into this, and it's possible to do, you can actually make a battery with homemade supplies. I'm not going to teach you how to do that today because it gets a little complicated and a little dangerous. Thankfully, over the last 220 years, scientists have worked very hard to make batteries much, much safer to handle and utilize for stuff and things. But to give you an example of how a loop works, I just happen to have a battery that I wanted to show you. See, is that in the picture? There it is. And it has a positive and a negative on it. And I have these little wires with clips on them. So I can clip them to the battery. Let's see, can I get that in there a little better? You know what? I'm going to bring the camera a little closer so you can see what's happening. There it is. So you'll be looking at my hands, not my face, but you'll get to understand and see better what's actually going to occur. So what I have here is some wires. I'm going to make an electrical loop using these clips and these wires. I'm going to connect them to an LED light and see if I can get this light to turn on just by closing the circuit. So what I have here is two wires, a wire going from the battery to the light, a wire going to nowhere, and a wire going from the battery. So this is going to be our proverbial light switch. So when I put these together, it should light up that light bulb. Let's see if it does. Oh, did you see that? Oh, it only did it for a second. Unfortunately, these LED lights are very fragile. So they will light up for a second, but then they will turn back off again. Let's try one more time. See if I do it this way, if it does anything. Nope, but I think I burned that one out, but I do have extra LEDs, so let's try another one. Let's see. If I connect these, turn on the switch, will that light turn on? What do you think? Let's see. Not that time. They do only work in one direction, and unfortunately, LEDs are not marked which direction. So you just have to kind of guess. So let's see what happens here. It turned on, only for a brief second. Did you see that blink though? That was kind of cool. Okay, so that's basically how a circuit works. You have electricity flowing in a continuous loop, transferring electricity to the devices you need electricity transferred to, whether it's your, here we go, it's me again. Whether your electricity is powering a light bulb, ceiling fan, a radio, the TV, whatever, you have to have that circuit of electricity, and the switch controls it, turning it on and off. So you definitely want to use those switches, especially the ones on the outside of the house if you're ever going to mess with stuff, because you need to interrupt that electrical flow to make it safe to replace things. Now, this is where the fun experiment comes in handy. I am going to make a circuit using a lemon as my electrical source. Can it be done? What do you think they did 220 years ago? When they didn't have batteries you could buy at the store, they had to use science and physics and other fun things. So with a lemon, you can get these kits called lemon clocks. And I've done a lot of experimenting in the last 2 weeks trying to recreate this. And I've learned it's hard to do. But if you have the kit, here's an example of one, the lemon clock kit, blah, blah, blah. Comes with, not a lemon, but it comes with pieces of metal. Remember that Voltaic stack we were talking about? Where you stack copper and zinc strips together with an electrolyte in between, creating your electrical charge. So I have a kit that came with copper and zinc strips of metal. Now what I do is I take my lemon, and I'm going to go back down here so you can see what I'm doing. Take that lemon, cut it in half. Now you can see it's just a lemon. There's no hidden battery inside of there. But if you take a copper and a zinc strip and you insert them into the lemon and connect them with a wire, you are now connecting the copper and the zinc to two separate pieces of lemon using a wire, and then you take another piece of zinc, stick it in the side that has the copper in it. Now there's a chemical reaction occurring inside that lemon with the copper and the zinc strips. And if you take another copper strip and put it in the side that has the zinc strip in it, now there's a chemical reaction occurring between the copper and the zinc on that side. Now how do we connect this loop? Well, the kit comes with a handy dandy little LED watch piece. It's just part of a watch. And theoretically you can do this with an old, say you had an old little plastic My Little Pony watch or something like that. Theoretically you could do it, but the connections on the inside, that's where it gets tricky. So this one just happens to have a watch that has the wires hanging off of it, which makes it so much easier to do. So what I do, and hopefully you can see the watch face. Let's bring it back to where you can see the watch face. Maybe a little closer. Yeah, not going to zoom in much closer. So if you take these wires and you connect them to your lemon battery, that watch should turn on. Let's turn this around, because there's definitely an order to how this works. The red connects to the zinc. Let's connect that in there. Tie it on. Hopefully it's a good solid connection, because this is tiny, tiny wire. And the black connects to the copper on this side. Can you see it? Did it work? It didn't work. Let's see what we're doing. Maybe we're a little loose. Science is never perfect, and it definitely takes a lot of practice. But it's supposed to work. You know, it worked yesterday. It's not working now. Maybe this lemon is dry. Maybe that's the problem. Well, by golly. Maybe if I switch it, maybe I got the directions wrong. Maybe I need to switch the wires. Because electricity likes to travel in one particular direction. It definitely has a preference. Oh, and my strips also have a lot of sticky stuff because I used duct tape once when I worked on this. And that might be causing an insulating barrier. Nope, that's not doing it. Does this work? I had it backwards. Look at that. Can you see the numbers on the clock? You probably can't. I wish I had 4 hands right now. And then I could show you how to do this. There it is. Can you see that? Let me see if I can, maybe I can pick it up and show it to you. It's a very not portable battery we have right here. This is where my assistant would come in handy. There's the clock, and it's working. See, there's the numbers on there. And if I let go of the wire, the numbers go away. Maybe I can figure out a way to hold this all at one time. keep trying. Hold on. Maybe I can lift the whole plate up, and that'll work. Now it's all twisted around. All right, connecting the wires again to our lemon battery. Nope, I got them backwards, of course. That's what makes it even harder, because when you move the wires around, the whole thing kind of flippy-floppies. That's one of my favorite scientific terms. There we go. Okay, so there. Can we focus? There's the watch working. Disconnect the battery. The watch turns off. Put the wire back on very carefully because it's very delicate. And it turns back on again. See? How cool is that? And it's just a lemon doing all the work, making electricity happen. Now, I did try to do this exact same thing with one of these LED lights. Apparently, while a lemon does have a chemical reaction occurring, which sends electricity through these wires, it's not quite enough to power one of these LED lights. It's a very faint amount. So you'd have to really get creative and experiment quite heavily in order to get it to power anything stronger than a cheap little LED watch. But what's actually happening here? What is the science behind what we've just done? Well, there's chemical energy stored inside the lemon, just enough chemical energy to power an LED watch. There is a chemical reaction that occurs between the steel, it's actually steel, not zinc, I take it back. Chemical reaction occurring between the steel, no, it is zinc, I'm sorry. Between the zinc and the battery, the lemon. Let's try that again. There's a chemical reaction occurring between the zinc and the lemon juice. There's also a chemical reaction occurring between the copper and the lemon juice. And this is causing the electrons to move. And what happens is the electrons get pushed through the wires. Because the two metals are different, the electrons get pushed in one direction. And it looks like it's pushed from the zinc to the copper, through the wire to the watch, and then back into the zinc, into the copper, over to the other lemon, and it creates a circuit by pushing those electrons. Now, if the metals were identical, if we had 2 strips of zinc in here, or 2 strips of copper in there, nothing would happen. Because the metals are equal, the electrons wouldn't go anywhere. But because they're different types of metal, and specific types of metal that react appropriately with the acid and other stuff inside of a lemon, the electrons are pushed and forced to move, thus creating a circuit which powers that cool little clock. And that is how electric circuits work, and that's how you can make one with a piece of fruit. Pretty cool. Just think about it. 220 years ago, when Mr. Volta was doing his experiments, how did he figure this stuff out? How many pieces of fruit and how many sticks of metal did he have to smush together to try to get that electric current to do anything? Boggles the mind. But here we are 220 years later, and we have these little batteries that run our cell phones for days, that run entire cars on the highway. It's pretty amazing how far we've come with our understanding of electricity and how to create and maintain electric currents. Well, this has been another edition of MAIN-iac Science Labs. I hope you learned something today. I hope you had some fun, and please don't take apart your dad's flashlight trying to figure out how it works. Ask him to show you. I'm sure he'd like to. I'm Mr. Randy. I'll see you again next week for more science.